A sunspot has just rotated into view that spans an area larger than 12 Earths side by side. That is not a metaphor. That is a direct measurement, and it is currently pointed almost straight at us. Stakes first. Sunspots this size don't sit quietly. They are the staging grounds for the sun's most violent eruptions, the kind that can knock out power grids, scramble GPS, and put satellites at risk. In the next few minutes, you're going to see exactly why this one matters, what history tells us about spots this size, and what to actually watch for in the coming days. This will take about 11 minutes. Let's get into it. Start with the basic question. What are we even looking at? A sunspot is not a hole and it's not damage. It is a patch of the sun's surface where a knot of magnetic field has punched up through the churning plasma below, and, in doing so, suppressed the convection that normally carries heat to the surface. That is why it looks dark. It isn't cold in any absolute sense, it's still thousands of degrees. It's just cooler than the blistering material around it. Cooler, relative to hell, is still hell. That's the joke solar physicists make, and it's not far off. Here is the single most important thing to understand about size. The bigger the spot, the more twisted and stressed the magnetic field underneath it has to be to hold that structure together. Think of it like a rubber band. A small spot is a rubber band with a little bit of a twist in it. A spot spanning 12 Earths is a rubber band wound so many times it's fighting itself, storing enormous energy, waiting for a reason to snap. That snap, in solar terms, is what we call a flare. And sometimes, attached to that flare, the sun throws off a piece of its own atmosphere entirely, a coronal mass ejection. 1 billion tons of magnetized plasma hurled into space at 1 million miles an hour or more. Now bring that back to the spot we're tracking. Solar physicists classify sunspot groups by their magnetic complexity, using a system that ranges from simple, orderly configurations up to what's called a delta configuration, regions where opposite magnetic polarities are crushed together in the same shared cluster, close enough to touch. Delta spots are the ones that produce the sun's strongest flares, the X-class events, the ones capable of measurable effects on Earth's technology. A spot large enough to hold 12 Earths has more than enough room and more than enough magnetic complexity to develop exactly that kind of delta structure. That is why size alone, while not a guarantee of an eruption, is treated by forecasters as a serious yellow flag. Let's pause on the hype for a second, because this is where a lot of coverage goes wrong. A big sunspot does not mean the sun is about to explode. It doesn't mean a flare is guaranteed. Plenty of enormous sunspot groups rotate across the solar disk and produce nothing more than a few modest flares before decaying quietly. So no, this isn't a doomsday signal. But here's the more concerning, more grounded version of the story, the one that doesn't need exaggeration to be worth your attention. Size correlates with potential energy, and a region this large, now facing Earth directly, is exactly the geometry you need for an eruption to actually reach us, instead of harmlessly sailing off into space in some other direction. That is the real story. Not just physics, geometry, and timing lining up. Consider what happens when that geometry does line up, because we don't have to guess. We have precedent. Go back to September of 1859. A sunspot group, later measured by observers of the era to be enormous by the standards of any century, produced a flare witnessed directly through a telescope by an astronomer named Richard Carrington, the first time a human being had ever watched a solar flare happen in real time. Within about 17 hours, the coronal mass ejection associated with that flare slammed into Earth's magnetic field. What followed became known as the Carrington event. Telegraph systems across North America and Europe surged with induced current so strong that some operators reported their equipment sparking and catching fire, even after being disconnected from batteries. Auroras, normally confined to polar latitudes, were reported as far south as the Caribbean. People in the eastern United States said the night sky glowed bright enough to read a newspaper by. That was 1859. We didn't have a power grid the way we have one now. We didn't have satellites, GPS constellations, undersea data cables. or a financial system that runs on synchronized digital timestamps. That is why the Carrington event, harmless in terms of human life at the time, is treated today as the reference case for a worst-case scenario. In 2012, a solar eruption of comparable magnitude to the Carrington event actually left the Sun. It crossed Earth's orbital path. We know this because a NASA research spacecraft happened to be sitting almost exactly where Earth would have been, and it recorded the storm passing through. The only reason it wasn't a global headline is that Earth, at that moment in its orbit, simply wasn't there. 9 days. That's how close the timing was. 9 days between a direct hit and a near miss, so clean it barely made the news. Connect that back to the spot rotating toward us right now. It doesn't need to match Carrington to be disruptive. Even a moderate X-class flare, paired with an Earth-directed coronal mass ejection, is enough to cause real, measurable problems. In March of 1989, a strong geomagnetic storm induced currents in the Hydro-Quebec power grid, strong enough to trip protective relays, and within about 90 seconds, 6 million people lost power across the province. Not for an afternoon. For hours, in some areas longer, in the middle of a Canadian winter. That is what a mid-tier event can do to modern infrastructure. And that event came from a Sunspot group that, while significant, was not even the largest on record. So let's talk about what large actually means in numbers, because vague words like huge don't tell you anything useful. Sunspot area is measured in millionths of the Sun's visible hemisphere, a unit astronomers call millionths of a solar hemisphere. A spot covering the surface area of 12 Earths registers at roughly 2,000 of those units, a genuinely massive reading, one that places it among the larger active regions tracked in the current solar cycle. For comparison, an average sunspot group might register anywhere from a few dozen to a few hundred units. This one is an order of magnitude past typical. That number, on its own, tells forecasters at agencies like NOAA's Space Weather Prediction Center to start watching that region closely, checking its magnetic classification multiple times a day, because size at this scale is the raw material eruptions are made from. Now, the part that always comes up in the comments, so let's address it directly instead of dancing around it. No, this is not a sign of an approaching pole shift. No, this is not evidence of some hidden planetary alignment conspiracy. And no, a sunspot facing Earth is not connected to earthquake activity, no matter how many viral posts insist that it is. Solar activity and seismic activity operate on completely different physical mechanisms. One is driven by magnetic reconnection in a plasma nearly 100 million miles away, the other by tectonic stress accumulating in rock beneath your feet. They don't talk to each other. What we're describing here doesn't need embellishment to be worth your attention. The real mechanism, magnetic energy, stored and then released, aimed by orbital geometry, is unsettling enough on its own. And it has the benefit of actually being true. So here's what actually matters for you, practically, in the days ahead, broken down into what to watch. Number 1. The region's magnetic classification. If space weather forecasters upgrade this spot to a delta configuration, that's the signal that the odds of a major flare have gone up substantially. That reclassification is usually the first real warning sign, well before any visible eruption. Number 2. X-ray flux readings from NOAA's satellites. Flares are graded on a letter scale, B, C, M, and X, each roughly 10 times stronger than the last. An M-class flare is a shot across the bow. An X-class flare, especially a large one, aimed at Earth, is the scenario worth genuinely paying attention to. Number 3. Coronal mass ejection speed and direction, once one is detected. Not every flare produces one, and not every ejection is Earth-directed. The ones that matter are the fast ones, moving at 1,000 kilometers per second or more, launched on a trajectory that intersects our orbit. Number 4. Geomagnetic storm scale, once material does arrive. This is graded G1 through G5. G1 gives you extra aurora at high latitudes, and basically nothing else. G4 and G5 are the tiers where grid operators start taking protective action, where airlines reroute polar flights, and where satellite operators brace for possible orbital drag and signal disruption. Number 5, and this one's for you directly. Your own GPS and your own power. If you live at high latitude, a strong storm can degrade GPS accuracy for hours. If you're on a grid with older infrastructure, a severe storm is the kind of event that can, in rare cases, contribute to voltage instability. None of this is likely on any given day. But this is the week the odds are elevated, and elevated odds are exactly what forecasters are built to track. That brings us to where this actually goes from here. This sunspot will remain facing Earth for roughly another week to 10 days, before the sun's rotation carries it around to the far side, out of direct alignment. That window, the time it's aimed at us, is the period that matters most. After that, even if it does erupt, the geometry changes, and Earth is no longer in the most likely line of fire. So this isn't a permanent, ongoing threat. It's a temporary alignment, and alignments like this are exactly why solar physicists watch the sun continuously, instead of only reacting after something happens. Here is the single most important thing to take from all of this. We live next to a star that occasionally rearranges its own magnetic field violently enough to reach across 93 million miles of empty space and touch our infrastructure directly. That is not science fiction. That happened in 1859. It nearly happened again in 2012. It caused real blackouts in 1989. The sun doesn't need to be malicious for this to matter. It just needs to be itself, at scale, aimed the right way, at the wrong time. And right now, for the next several days, one of the largest active regions of this solar cycle is doing exactly that. Watch the classification, watch the flux. Those two numbers, more than any headline, more than any dramatic photo of the sun, will tell you whether this becomes a footnote or becomes a moment people remember. The way they remember Quebec in 1989. Stay with this channel, because when either of those numbers moves, we'll be the ones breaking down exactly what it means before anyone else translates the jargon for you. If this kind of forecasting under pressure content is useful to you, subscribe, hit like so this reaches more people before the window closes, and share this with anyone you know who still thinks space weather is something that only matters to astronauts. It doesn't. It matters to your grid, your GPS, and your week. Stay alert, stay informed, and we'll see you in the next one.